Mean value theorem, unit 5, I think. We're all the way to unit 5. 2 more get-ups until break, so we are getting close. Mean value theorem. Well, let's start with some basic stuff here. If you drive 72 miles in 1.2 hours, what was your average speed? So how would I find that? Should have made the numbers easier. How am I going to find average speed? Yep. I mean, you can just use the units, right? 72 miles divided by 1.2. 72 miles divided by 1.2 hours. 72 divided by 12 is 6, so this is 60 miles per hour. So again, this is if you look at your odometer and it's gone 72 miles in 1.2 hours, your average speed was 60 miles an hour. Does that mean that you drove 60 miles an hour for the entire drive? No. Does it mean that at some time you were driving exactly 60 miles per hour? That's the heart of the MVT right there. It's like, does it mean that? It does mean that. It does mean that. And the only way it could not mean that, or the way around that, would be if you could like time travel, like jump places. I guess that's not time travel. That's just immediately land somewhere else and have no time expire. Then maybe you could not go 60 miles an hour. But because miles per hour is continuous, there's a word. If you're going to get from 0 to 75, you got to go through 60. There's no other way. You can't jump past 60 in a car. Maybe sometime later in the future, you could go from 0 to 75 like instantaneously, but that doesn't work. In fact, I don't think you could even do it in the future. You got to go through 60 to get there. I think this one's a little easier. Could there have been more than one time during your drive you were going exactly 60 miles an hour? Definitely, right? It might have been the whole time. You could have just been going, had the cruise control set on 60. More likely it was a little above, a little below, a little above, a little below, and so the average was 60. And you went 60 a bunch of times. So there must have been at least one time when your instant speed was equal to your average speed. This is the Atchafalaya Bridge problem. They'll measure your average speed because they can tell how long it took you to, right? They have markers on the bridge, so they already know they have a fixed distance. And if it takes less than 18 minutes, then your average speed is greater than what they're okay with. And that means at some point, your instant speed was equal to your average speed, and therefore you were speeding. We're really close to calculus. Well, here it is. Average rate of change, AROC, is the slope between 2 points. Delta y over delta x. y2 minus y1 over x2 minus x1. Or in our case, d2 minus d1 over t2 minus t1. Change in distance over change in time. That's our average rate of change. Sometimes I will, not mistakenly, but I will sometimes call this the algebra rate of change. Like the A means average rate of change, but you find it by using an algebra rate of change. It's an algebra slope. So there are questions on the AP exam once in a while, like it's an easy multiple choice one if people are paying attention, where it will ask for an average rate of change, and you got to keep your brain turned on. You're like, wait a minute, that's not even a calculus question. It's calculus words, I guess. But if it asks for average rate of change, that's an algebra 1 thing. Just what's the slope? Instantaneous rate of change, that's a calculus thing. That's a calculus slope. Slope of the line, tangent to the curve, dy dx, instantaneous velocity, miles per hour, however you want to phrase it. That's the calculus slope. How fast are you going right now? And so the mean value theorem says that given the right conditions, we'll talk about those in a minute, basically differentiable and continuous, instant slope equals average slope. How I will usually say it is that the calculus slope equals the algebra slope. At some point. Right? Maybe not the whole time. You weren't going 60 the whole way, but at some point you were going 60. At some point crossing the Atchafalaya Basin Bridge, you were speeding. If your average speed was speeding, then your instant speed was at some point speeding. Maybe multiple points, but at least some point in there, you were speeding. See if I can draw a picture. I used to have a good popsicle stick for this. I guess I'll make a new one. Not a popsicle stick for calling your name, but for illustrating what we're about to do. So draw a sketch kind of like mine. It doesn't have to be exactly like mine, but kind of like mine. And let's say this is point A and this is point B. And let's see, instant slope. Let's draw it first. So let's draw a picture of the average slope from A to B. So instantaneous slope at A would be a tangent line at A. Instant slope at B would be a tangent line at B. That's not what I want. I want an average slope from A to B. Okay, that's just good old algebra 1. Change in y over change in x. That's my slope. That's my algebra slope. Algebra slope. y2 minus y1 over x2 minus x1. Mean value theorem says that somewhere on the curve, in between A and B, maybe more than somewhere, but at least somewhere on the curve, the instantaneous slope, the calculus slope, the tangent line, is the same. So there's my algebra slope. I think my tangent line slope is the same right about there. That's my calculus slope. Maybe I should label it on the paper rather than just on my popsicle stick. Calculus slope, dy dx, is somewhere equal to the algebra slope at least in one spot. Is there another spot where it's equal? You see another tangent line location? Probably right around there somewhere. Again, we're just eyeballing right now. But somewhere in there, there's another spot where the calculus slope is equal to the algebra slope. We'll usually call that f prime at C. F prime at C. Where C is the x value. I don't know where it is, but there's some C some C on A to B, well, I mean, some C between A and B, where f prime of C equals y2 minus y1 over x2 minus x1. That's MVT. Calculus slope equals algebra slope. So the most shortest, easiest way to remember it, it doesn't have quite all the details in there yet, but MVT tells you that calculus slope equals algebra slope somewhere on the interval. Sometimes we overlook the somewhere on the interval part, like crossing the bridge. The average speed equals the instantaneous speed somewhere on the bridge. Like that doesn't guarantee that you were going 75 miles an hour after the bridge or before the bridge. Like who knows what you were doing before or after. But on the bridge, if your algebra slope is 75, then somewhere you were going 75. Maybe lots of somewheres. Right, again, a not quite to calculus example. A car that is equipped with an easy tag drove through a toll booth at mile marker 226 at noon. I'm trying to organize my information here. So at noon, we were at mile marker 226. Then through a toll booth at mile marker 326 at 1:15. The speed limit is 70. A few days later, the driver received a speeding ticket in the mail. How did he get caught speeding? Would this hold up in court? Let's figure out the average speed, right? Because like they could take a picture of your license plate and they can know that if you made it from mile marker 226 to 326, that your distance was 100 miles. Or your change in distance, I should probably say. And your change in time, let's see, an hour and 15 minutes. Let's put that in hours. 75 minutes, but I don't want minutes. I want miles per hour. So what is an hour and 15 minutes in hours? 1.25 hours. So 100 divided by 1.25. I don't have a calculator up here. What do you get? 80. So that means this person's average speed was 80 miles an hour. So he might go to court and say, you never put a radar gun on me, no cop was out there. And the judge is going to say, well, let me give you a lesson in calculus, young man. Your average speed was 80 miles an hour, which means somewhere you were going 80 miles an hour. Maybe lots of somewheres, but at least somewhere you were going 80 miles an hour. How did he get caught speeding? MVT. Should this hold up in court? Yes. Okay, so that's the less technical version. Now we're going to get to a little bit of technical. MVT. If f of x is continuous. Okay, so if your path on the bridge is continuous, meaning you don't get to like teleport. That's the word I was looking for earlier. Right? You can't teleport to the end of the bridge and back and forth, right? Because then that would mess things up. So assuming it's continuous and differentiable, meaning it's kind of the same thing. You can't. Your speed is smooth. You can't jump from 20 to 50. Like you got to go through all the ones in between there. There must be at least one number c between a and b such that calculus slope equals algebra slope. All right, so don't get lost in all the letters. F prime of c equals f of b minus f of a over b minus a. Like, what that says is the calculus slope equals the algebra slope. And I guess we should be a little more specific. The calculus slope at C equals the algebra slope overall. So here's one way to say it. dy dx equals delta y delta x. This is kind of the same thing. dy dx is calculus, delta y delta x is algebra. So MVT is, if it's continuous and differentiable, then calculus equals algebra. Calculus slope equals algebra slope. Okay, finer points that usually are not usually tested is that it has to be continuous on the closed interval and differentiable on the open interval. This gets discussed multiple times per year in the Facebook calculus teacher group. You don't want to know the discussions, I'm assuming, because every year the main administrator links to this long thing about why it works. It's like, oh, that's beyond what I want to worry about. Continuous always goes with closed, like the C's go together. That's just how I remember it. And the differentiable goes with the open. So you've got to say that if you want to use MVT. And usually it's something that is a polynomial, so you'll know it's continuous. Or if it's not continuous, like look at number 2. Skipping ahead a little bit here. So that's not continuous, but where is it not continuous? Like, there's only one spot that's a problem. Looking at number 2, where is that thing not continuous? At x equals 1. So as long as we're away from x equals 1 on either side, we'd still be okay. But if our interval, whoops, we can go ahead and answer number 2 now. This is a trick question. How many values of C are guaranteed by the mean value theorem for h of x on the interval 0 to 3? Yeah, this is what you need. Well, it's not continuous at x equals 1. Which means it's not continuous on the interval. So we're kind of done. MVT doesn't work. Therefore, can't use MVT. So I guess we still need to answer the question. How many values of C are guaranteed? So no values are guaranteed because we can't use MVT. So it's got to be continuous, got to be differentiable. Back up a second here. Jumped ahead of myself on that one. Differentiable, just a reminder, that means no discontinuities. No discontinuities. What else makes something not differentiable? A cusp. So no cusp or sharp turns. Thank you. And one more thing, this one's maybe a little bit tricky. No vertical tangent lines. Hey, that was... All right, function must be continuous. We said that. Function must be differentiable. And then C has to be between A and B. Occasionally you're gonna do the math on these and you'll get a C. Like, you're guaranteed to get a C between A and B, but if you get more than one value, the only values you can sort of report or say are the ones between A and B. Let's work that, and we'll see what happens. Okay, examples. If g of x is x to the 2/3, find all values of c which satisfy the mean value theorem on the interval 0 to 8. That doesn't look like it has any. I can plug in anything, so I know it's continuous. That doesn't have any jumps or anything. So I can say g of x is continuous. It's continuous everywhere, so it's certainly continuous on 0 to 8. Alright, I'm going to give you the graph of this one, because this one illustrates that subtle difference between the open and closed thing. Because the graph looks like something like that. So g of x is differentiable. It's not differentiable at 0 because there's a sharp turn there, but that's why we have the open brackets or the open parentheses. It doesn't have to be differentiable at 0. As long as everywhere else it's okay. So that's like the really unique problem that tests that difference between a bracket and a parentheses. It's continuous. It's not differentiable at 0, but it doesn't have to be differentiable at 0 because we don't want to include 0. Okay, so therefore MVT applies. So you have to state your conditions. That's the if. And so if this is true, MVT tells us that, I'm going to just write it in words, the calculus slope at C equals the algebra slope. Now there's a lot of work to go in to find the calculus slope at C and to find the algebra slope, but this is the big picture roadmap we're going with. Let's do algebra slope first. So that's change in y over change in x. So let's find f of 8 and f of 0. So 8 to the 2/3. Cube root of 8 is 2. 2 squared is 4. 0 to the 2/3, that's easy. So change in y, y2 minus y1. Change in x, x2 minus x1 is 1/2. So there's my algebra side of the problem. Now I need to go find the calculus side of the problem. So how do I find a calculus slope? What does calculus slope mean? Take a derivative. So I need the derivative of g. So that would be 2/3 x to the negative 1/3, power rule. So my calculus slope is 2/3. I could write x to the negative 1/3, but it might be easier if I did the cube root in the bottom. It might help me when it comes to solving this thing. Okay, well now let's solve it. Probably cross multiply would be my best bet here. So 4 equals 3 cube root of x. So 4/3 equals the cube root of x. So x equals 4/3 cubed. I need to check 4/3 cubed. Is that between 0 and 8? Oh, that's maybe kind of tricky, because what's 4/3? 1.3. 1.3 squared. I don't think that's even 2 yet. And 2 times 1.3 is 2.6. So no, it's not. It's definitely between 0 and 8. Actually, because 2 cubed would be 8. So anything less than 2 cubed would be less than 8. So I'm good with 4/3 cubed. I suppose if I really wanted to see that, that would be 64 over 27. And that's between 0 and 8, right? 64 over 27 is 2 and something. So my answer is 4/3 cubed, or 64 over 27. That's the location. Right, so that's the end of the problem, but if we wanted to see it visually, there's my algebra slope. And then at 64 over 27, there's my calculus slope. Algebra slope equals calculus slope. So MVT, if it's continuous and differentiable, then calculus slope equals algebra slope somewhere on the interval. All right, we already did number 2 because we threw it out because it didn't meet the criteria. You definitely have to check the criteria, because if you don't check the criteria and you just start this problem, well, congrats. Now you get to do a quotient rule problem, and you have to find the algebra slope, and you're going to get an answer. Like, it's going to work. It's not going to work at the end, but you're going to get an answer, and you won't know till the very end that you did something wrong. So check your conditions, because we throw a few in there where it just doesn't work, so you don't have to do anything other than tell me why it doesn't work. Number 3, find all values of C guaranteed by the mean value theorem for y equals cosine of x on 0 to 4 pi. Okay, cosine of x, that's this thing. In fact, from 0 to 4 pi, that's 2 cycles of it. I need to state the conditions. You can't just jump right in. You have to state the conditions. So y is continuous on the closed and differentiable on the open. Right, because cosine is always continuous and always differentiable. So it wouldn't matter what interval we picked. We would be good to use the mean value theorem here. Therefore, mean value theorem applies. The mean value theorem tells me that the calculus slope at C equals the algebra slope overall, the whole thing. So again, you got to do the 2 pieces and then set them equal to each other. So you go do some algebra slope work, and it's your algebra 1 problem, and then you do the calculus problem where you take a derivative, and then you set them equal to each other, and then you've got another algebra problem to work. So let's do the algebra part first. So cosine of 4 pi. Let's see, that's around once, around again. Cosine of 4 pi is 1. Cosine of 0, so don't go anywhere, also 1. What's wrong? Remember, cosine is the x-coordinate. We good? At pi over 4, the cosine is root 2 over 2. Okay, so algebra slope is 1 minus 1 over, I guess it doesn't matter after that point because that's 0. 4 pi minus 0. 0 over 4 pi is 0. Okay, so my algebra slope is 0. I suppose if I had taken the time to could have drawn it like that. There's my algebra slope. Alright, calculus slope. So if y equals cosine of x, then y prime is derivative of cosine, negative sine of x. So sine of x equals 0. Where does that happen? Now my graph's misleading because that's the graph of cosine. So don't go looking at that graph if we want to find where sine of x is equal to 0. So where's sine of x equal to 0? 0, but where else? And where else? And where else? Because we got to go 3 pi and 4 pi. Okay. Well, it also is there at 5 pi and 6 pi and 7 pi and 8 pi and 9 pi. Why can't I use 5 pi, 6 pi, 7 pi? It's not in my allowed. It's not between 0 and 4 pi. So I have to throw it out. Now, I need to be careful. I didn't emphasize this earlier, and now I'm seeing why it matters. Very back at the top. So the function must be continuous on the closed, differentiable on the open, and then the c value is also on the open. So continuous on the closed, the c's go together, the other two are open. So this means I can't include the endpoints as part of my answer. We're picking problems where these weird things show up. So I can't include 0 and 4 pi. Only pi, 2 pi, and 3 pi are on the open interval 0 to 4 pi. Open interval meaning don't include the endpoints. So you can't have endpoints for an answer to an MVT problem. So there's 3 intervals you have to worry about. It's got to be continuous on the closed, the c's go together, differentiable on the open, and then the answer has to be on the open interval. So that's why I had to throw out. So it was obvious to throw out 5, 6, and 7 pi, a little less obvious to throw out 0 and 4 pi. Number 4. Number 4 and final. Selected values of f and g are given in the table. F and g are both differentiable functions. Explain why there must be a value of x such that f of x equals 0. So I want f of x to be 0. Let's see. How would I know that f of x is 0 somewhere? Or where would it happen? Ian? Okay, so yeah, the x values are between 1 and 3. The y values between -2 and 5. I like that. How do I know that it's actually in there? How do I know it didn't go from, let's see, 1, -2 to 3, 5? How do I know it didn't, I don't know where it's 0. How do I know it didn't do this? Right? And there's not a 0 there.
Because it's differentiable and therefore it has to be continuous.
F of x is differentiable. therefore continuous. Therefore that picture I drew couldn't be true. So this is the intermediate value theorem. There's a 0 in between -2 and 5. All right, so this is where we say the y value is in between there. F of 1 is less than 0 is less than f of 3. And you can put either one of those statements. You can do the f of -1, you can do the sort of function values, or you can actually just plug in the values and say 0 is between -2 and 5. Therefore, remember this is where you just have to write it out, there is an x between -2 and 5. Whoops, those are the y values. Between 1 and 3, where f of x equals 0. That's IVT. So that's IVT. Intermediate value theorem. So that's a throwback theorem. If it's continuous, and if the y value is in between the y values, then the x value is in between the x values. So that's a review problem there. IVT. Explain why there must be a value of x in 4 to 9 such that g prime of c equals 1. Okay, well this is talking about derivatives, so I don't think this is IVT anymore. I think this is probably MVT. So MVT, I need to say, let's see, f and g are both differentiable. So g is continuous on the closed interval. The c's go together, continuous on closed. Differentiable on the open, because it's differentiable everywhere. We should say that. Continuous because it tells us it's differentiable. But I need to go ahead and say those, that way I can use the MVT. Continuous on the closed, differentiable in the open. Therefore MVT applies. And MVT, again, always use the words first. This probably wouldn't get you any credit if just saying the words, but if it helps you get there, the calculus slope equals the algebra slope. Okay, the algebra slope between 4 and 9, so I need g of 4 and g of 9. This is just like algebra 1 stuff here. I got a table. Make sure you go to the right spot. G of 4 is 7. G of 9 is 12. So my algebra slope, 12 minus 7 over 9 minus 4. 5 over 5 is 1. Now the other side is maybe a little bit weird because I don't have an equation to take a derivative of. But the calculus slope of g is g prime, right? I don't know what g is. I don't have a formula for g. But all I'm asked to conclude is that g prime of c is equal to 1. So I'm there. Like the calculus slope of g, that means g prime of c equals 1. And then I can go ahead and say somewhere where c is between 4 and 9. And again, I don't want to include 4 and 9. The answer is on the open. So I don't know that I did calculus because MVT is calculus, but I didn't do any actual taking of derivatives because my conclusion was just that that derivative, whatever it looks like, equals 1 somewhere between 4 and 9. And the reason is, between 4 and 9, from 7 to 12, like I have no idea what the graph looks like, but the algebra slope is 1. So whatever we do to get there, who knows what this thing does, there's at least one spot, maybe 2 spots, maybe more, where the calculus slope is equal to the algebra slope. MVT guarantees that. Part C. Explain why there must be a value of C in the interval 1 to 9 such that f prime, so again, thinking MVT, is equal to 4. So let's do the same thing here. There it is. It's stuck on the sneeze. F is continuous on the closed, 1 to 9. Differentiable on the open, 1 to 9. Because it's differentiable. Like it's told us it's differentiable. So now let's do the slope. Well, let's slow down. MVT applies. Calculus slope equals algebra slope. The calculus slope is f prime c. The algebra slope is the algebra slope. So let's find the algebra slope from 1 to 9. F of 9 is 12. F of 1 is negative 2. So the algebra slope is 12 minus negative 2 over 9 minus 1. 14 over 8. Uh-oh, that's not 4, so hold on a minute. I've got a problem here. Because I want to conclude that the slope is somewhere equal to 4. Right now I can conclude that the slope is somewhere equal to 14/8. That's true, but I need to be able to say that it's somewhere equal to 4. So, if there's another spot, like we went from 1 to 9, and the slope was not equal to 4. If there was somewhere else between 1 and 9 that it was equal to, that the slope was equal to 4, we could use those instead. So this was a little bit tricky. So now I've got to really think here. So the slope between 1 and 9 was not 4. Is there a spot in here, like anywhere in there, where the slope is equal to 4? Because then I'll just use those points instead. What about 7? I mean, f is equal to 4 at 7, but I need a range, I need an interval where the slope is equal to 4. So I guess it's 1 to 3, that would be 7/2. That 3 to 4, that'd be 2. 4 to 7, that'd be 3 over, no, that'd be negative 1 even. 7 to 9, what about that slope? From 4 to 12 and 7 to 9, this difference is 8, this difference is 2, so that's 4. So this is an ugly problem because it forces you to go find a slope of 4 somewhere amidst all that data. And if it had really been cruel, it could have made it so that you had to like use 3 to 7 or 4 to 9. Instead, we'll use 7 to 9. So back to my problem. MVT still applies. I don't want to use this. I want to use 9 and 7 now. of 9 is 12. F of 7 is 4. I'm kind of just going to pick up where I left off. It's okay to mark that out. You don't have to erase it. If you draw a line through it, it's not graded. I'm not gonna, and the AP grader's not gonna be like, oh, they made a mistake. I'm gonna take off for that. Like, if you don't want them to grade it, mark it out. So 12 minus 4 over 9 minus 7, 8 over 2, that's 4. So that's the interval we were looking at. So f prime of c equals 4. And we could be more specific now, somewhere on 7 to 9, which also means somewhere on 1 to 9. That's a pain when they give you those, because you think there's a mistake in the problem, because you do 1 to 9, you're like, wait, that didn't work. And it's because there's other options. That's just cruel, is what that is. All right, let me pass out worksheet 1, and we'll do a few of them together, perhaps. Looking at 6 through 9. Maybe we'll do 6 and 7, and I'll leave 8 and 9 for you. How many values satisfy the mean value theorem for g of x on -3 to 6? Okay, well, it's continuous and differentiable everywhere, so MVT applies everywhere. Not worried about that. I'm worried about calc slope equals algebra slope. So algebra slope from -3 to 6. 1, 2, 3. So there's my -3. 1, 2, 3, 4, 5, 6. Okay, so here's where your straight edge might be helpful, or even a popsicle stick. There's my calculus slope. No, that's my algebra slope, excuse me. Right, for the endpoints. So the question is, how many values? So how many places have a calculus slope equal to my algebra slope? Let's see. I'm thinking 1 in here somewhere, 1 in here somewhere, and 1 over there. So I would say there's 3. You see how I did that? There's not even any math involved. I mean, it's math, but it's not finding derivatives. It's understanding algebra slope and calculus slope. All right, now that I've polluted my diagram with pen, I'm going to use a different color and answer the same question from 2 to 6. So from 2 to 6, there's my algebra slope from 2 to 6. I guess if you guys want to borrow popsicle sticks on the test, I will let you. So how many places satisfy the mean value theorem from 2 to 6? What do you think? How many places have a calculus slope equal to the algebra slope? I agree. I think it's 1. But what about this spot back here? Like that there's a spot back there that has a calculus slope equal to the algebra slope. What's wrong with that spot? It's not in 2 to 6. So there's other places, but MVT only guarantees 2 to 6. Then, yeah, your graph is going to be wildly messed up by the time you get finished putting all those dots on there for that one. Okay, that's a long enough video.